All right, howdy. Today we're going to talk about continuity. So there's a picture definition that just looks like this, that this function is continuous. All right, often they say you can draw it without picking up your pencil. And not continuous means there's a break. So for instance, it might look like this. Or, just a jagged edge, a cliff. All right, things like this are not continuous. Now, you can recognize this type and this other one as well of discontinuity because what happens here, if this is the point A and this is the point B, here's your function f, and this is the point C, well, you see here, you can determine that there's a hole in the graph using limits because the limit as x goes to a of f of x, well, your x is supposed to get closer and closer to a, and then you plug it into your f and see what happens, and f of x will be getting closer and closer to b. But the actual value of f of x, if you plug in a, is this c. And these are not the same. Okay? So whenever the limit of f of x as x approaches a is not f of a, that means there's some kind of break in your graph. The limit's what it's trying to get close to. The value is what the value actually is. And if they're different, it's not continuous. So here's the official definition of continuity. We say f of x is continuous at x equals to a if the limit as x goes to a of f of x is just f of a. All right? So here's the point. Continuous functions are the functions where you evaluate limits without any tricks. You just plug in x equals to a. So it's the place where you don't even need a limit. Just plug in. Okay? So that's what continuous means. All right. It's a kind of an easy theorem that if you have functions f and g that are continuous, then pretty much anything you do with them leaves them continuous. So for instance, f plus g is continuous. So if f and g are continuous, then so are f plus g, f times g, f over g, of course, when g is not 0. When g is 0, all bets are off. But as long as g is not 0, you're okay. And then finally, composition of functions. If you plug in f composed with g, remember that means f composed with g of x just means f of g of x. So you take f, g, and plug it into f. So pretty much anything you do with a continuous function, except division by 0, leaves it continuous. So that means if you want to evaluate a limit, and you can see that all the pieces are continuous, and there's no division by 0, then it's easy. Just plug in. So here's an example. Evaluate the limit as x goes to 1 of, let me tell you one more theorem first. All the functions that you know and love pretty much are continuous. Things like constant functions are continuous. Polynomial things like x to the n is continuous. Power functions like x to the r is continuous. Exponential functions, e to the x, 3 to the x, those are all continuous. Logarithms, obviously where they're defined for x bigger than 0, are continuous. Trig functions like sine of x, cosine of x, those are all continuous. So all the basic functions you know and love, are continuous. Anyway, let's do our example. So let's look at the limit as x goes to 1 of x squared e to the x plus sine x all over 1 plus x squared. Well, I look at this. Every piece, x squared, e to the x, sine x, 1, those are all continuous functions. So when I slap them together, they stay continuous. And I haven't divided by 0 because as x is going to 1, the denominator is getting close to 2, which is not 0. So to evaluate this limit, since everything is continuous, I just plug in 1 everywhere. So it's 1 squared e to the 1 plus sine of 1 all over 1 plus 1 squared. And that's your answer. Super easy because it's continuous. All right? You can ask problems like this in more complicated ways. For instance, find the value of c so that the function g of x, which is normally equal to, let's make it x plus 2 when x is not 0, and make it c when x is 0, so that this function is continuous. All right? Well, first of all, away from 0, this function is clearly continuous. So for x not equal to 0, x plus 2 is already continuous. We just need continuity at x equals to 0 because that's the only point missing. All right? So we must have the following. To be continuous at 0, you would have to have g at 0 being the limit as x went to 0 of g of x. Okay? And if we have that, then we'd have continuity at 0, which means we'd have continuity everywhere. All right, well, what is g of 0? Well, that was just the number c. And the limit as x goes to 0, well, what's g of x when it's getting close to 0, but not 0? It was given by x plus 2. All right? All right, so that's what I need. The limit of x plus 2 as x goes to 0 is the value for c that we need. So if you calculate this limit as x is going to 0, then x plus 2 is going to 0 plus 2, which is 2. So we need c to be 2. And that will make g a continuous function. All right, that's it. Ciao.